Hello, everybody, and welcome to episode 39 of I Wish You Were Dead, a podcast about things that used to be alive. I am recording with my regular laptop, but that is Gavin over there. Gavin, how are you doing today?
I'm doing pretty good. Welcome back to school, most people, by this point, including Mike.
Yes, and
Mike
by the
Mike
time
goes
you
back
guys
to
are
school
hearing
tomorrow.
this,
Well, today, at the time you
yeah,
hear this.
today, by the time you guys are hearing this, this will be today. I'll be back at school. I have two classes of sophomores that I'll be having this Wednesday, and I'm excited to finally be back. It's gonna be weird and we're not entirely sure what all the rules are going to be like this year, but I am excited to be back and teaching slightly more normally than I have been for the last year.
Yeah, and it's sort of weird the opposite for me because this is the first fall semester in the last actually my entire life, realistically, that I'm not
Hmm.
going to school, and that hasn't
Yeah,
really
yeah. I
sunk in yet.
There was a period of time before I knew I was going to be a teacher where I thought about that, like at some point I'm not going to be doing this. Like I'll just have a job, and then and then I die at some point. And then once you become a teacher, it's like, oh no, you have that experience every year of going back to school and after having a couple of months off. So it's a blessing and a curse, but I think any teacher that gets defensive about having a few months off in the
Right.
middle of the year
Yeah.
is they're lying to somebody, themselves or somebody else, because it's a pretty sweet deal.
Yeah, and that's why I'd really love to end up like teaching at a university as well. But we'll
Right,
we'll
that'd be
cross that
perfect.
bridge when we come to it.
I'm sure we'll have a podcast episode whenever that happens.
Hopefully, yeah.
All right, so do we have a calendar for today?
We absolutely do. So,
All
do you
right,
have a year for me?
2016.
You actually got another one. Let's go.
Hey, that's two of them. All right.
Yeah, two for what,
I think they've both been
30?
2016, haven't they?
I think so. But that's what, two for about 30 roughly?
Like 35. I don't remember exactly when we started doing this, but yeah,
And then we've also had your three
I'll
episodes where
take
we
it.
didn't do it as well.
Yeah, that's just so look at that. My percentage is going even higher.
But yes, this is from September 8th, so that would be today. If you're listening to this the day it goes up, that would
Hmm.
be so September 8th, 2016, and the headline is 4 species of giraffe exist, not one.
4.
Yes.
Okay.
So
I guess that's not really surprising, but okay.
geneticists from I'm hmm, I'm assuming that this is pronounced Girth University, but it's spelled Goethe. It's in Germany. The only reason that I think that
Yeah,
it's
okay.
pronounced that way is because there's a mineral called Girthite that is spelled Goethite. So maybe from Girth
I,
University in Germany.
it's,
And also they had
it's
successfully
amazing they
analyzed the
let me
genetic
teach
code.
children because I'm just laughing so much at this.
Mike, relax. It's your last day before school. Actually, yes. Get it out now, please.
Yeah, yeah, that
Um,
now not in front of the children.
exactly. Anyway, geneticists from this university in Germany announced that they had successfully analyzed the genetic code of common giraffes and discovered that, contrary to previous beliefs, 4 genetically distinct species of the animal exist instead of just one. The team came to this discovery
Hmm.
through genetic examination of 190 giraffes found across Africa, including skin samples from each of the 9 previously recognized subspecies of giraffe. Following the identification of 4 distinct species, the team examined social behaviors of the groups and confirmed that giraffes from separate species are far less likely to mate and intermingle. Importantly, researchers believe that this finding emphasizes the need for renewed conservation efforts within the giraffe population, as individual species may be more at risk for extinction than giraffes are as a whole. So
Okay. I mean,
that brings up a very interesting conversation that we absolutely do not have time to get into, that we've talked about a little bit before, but it's like, what is a species, quote unquote? Like, what does that even mean?
yeah.
Like, I know what I mean, but what do you mean? Because there are so many definitions. It's not like, oh, if they are X% genetically different, they're a different species. There's no line to cross there. So it's like, how different is different enough genetically,
This
which
is
is why
sort of
I don't.
this is like
Mhm.
the Supreme Court's definition of porn, like we've talked about before. I
Yes,
know it when I see it.
but that's why I don't really like separating out species by genetics, because again, it's like, where are you drawing the line?
Would you prefer they be separated more by just like physical characteristics?
Yes, and this is
Okay.
absolutely the paleontologist in me coming out, because obviously that's how we do it. We don't have DNA, barring a couple of very very recent animals like mammoths and things like that. But um, all we have to work with are bones. So it's
Hmm.
that's all we get. So for me, that is usually good enough. For highly detailed things like human origins, where we also have a little bit of a stake in the answer, um, I think that's pretty much fine to use genetic stuff with. But like for giraffes, I think it's neat that they're doing the study, but I don't know. Granted, I haven't read the study. I think I would like to, though. That'd be an interesting study. But like I said, we don't have a whole lot
Yes.
of time to get into it, because this today is a really interesting, really important episode. And so, Mike, have you read the topic for today?
I did, and then I forgot it. Uh,
That's okay.
should I go back and look it up?
Yeah. Well, no, it's okay. So
Okay. Well, I went back and
today,
clicked on it, so now I know what it is again.
today we are talking about plate tectonics, which is the most fundamental theory in geology. And we will go
Before you even
into,
begin,
yeah,
can you explain to people what you mean when you say theory, just to make sure that it is
yes,
like define theory for the masses, please.
absolutely. And this is in the outline, but later on a little bit,
Oh, is it real? Oh,
but that's okay. Uh, it's good to get out of the way early, because so many people screw this up.
perfect.
Even a lot of people who like kind of understand science. Uh, so
Right.
in like common vernacular English, a theory is an idea, like a hunch, sort of, right? More or
Right.
less. People
Yeah,
like
like
Sherlock
unproven, but
Holmes.
it's an idea.
Right. Something like Sherlock Holmes would be like, I have a theory about how the murderer did this or whatever. That is not at all what a theory is in science. The common use of the word theory is much more similar to a scientific hypothesis instead, where it is, okay, you have
Exactly.
some data and you have a question about those data. Or you have a couple of observations and you have a question about those observations that you want to test. A scientific
Hmm.
theory is a hypothesis that has been tested and tested and tested and has so much data and observations backing it up that it is just taken as a scientific fact, or as close to a fact as you can reasonably get in science, because we don't like absolutes in science. Um,
Hmm.
so things
But
like,
one of those things where you need to have like a base, like, okay, at some point we need to stop trying to prove this thing correct and just take it for granted that this thing is true, and now we can move on from
yes,
there.
right. It is, things like gravity is a theory. We don't actually know, the exact forces and properties that cause gravity, but we know that it exists, and we know that it's due to mass and a bunch of other physics related things that, as I'll talk about in a minute, I don't understand a whole lot about physics. But there's the theory of universal gravitation. So gravity is quote unquote just a theory, but it has, as I think I talked about this in a couple episodes about evolution as well, but there is more evidence supporting evolution, and we understand evolution much better than we understand gravity. And plate tectonics is to geology what evolution is to biology, in that nothing else in geology makes sense together in the absence of plate tectonics. So you can study rocks, you can, you can pick up a rock on the side of the road and you can describe it. You can say it's got, X% quartz, X% calcite. It's, the grains are this big. You can do that perfectly well. But as soon as you try to figure out, okay, how did this rock get here? You understand nothing if you don't understand plate tectonics. So this is like the most foundational theory in geology.
And quick question for you, just about the
Yeah.
kind of culture that surrounds it. You mentioned evolution, and there are
Mm-hmm.
the scientific consensus being what it is, but there are still your fringe people that and I shouldn't say fringe. I think it's a larger movement than people might want to give it credit for. That say evolution's a lie. Is there any kind of a movement against plate tectonics the same way that that says this isn't real?
Not explicitly like that. It is very much implied by people like flat
Oh,
earthers,
okay,
because with the earth being
understood.
flat, it doesn't have an interior, which becomes very important to plate tectonics. So yes, but it's not like
Gotcha.
people are like, yeah, a lot of the other things about the earth make sense, but not plate tectonics. That kind of person specifically doesn't really exist.
Gotcha. Okay, that understood.
So, and I have this as the first bullet points on our agenda here. And there's an important caveat here, but it involves things that I don't really understand. So I'm conveniently leaving it out. But I would argue that the theory of plate tectonics is the most revolutionary leap in science, definitely since World War II, probably in the entire 1900s. I would put it like easily in the top like 3 for the entire 1900s. And the convenient caveat I'm leaving out is anything to do with space. Because I don't understand it. Obviously, the revolution in technology to get to like the moon, yeah, like in engineering technology to get us to the moon, obviously that was super, super important and incredible. But I don't know how much of a leap like the engineering had to actually take, or whether it was just like, hey, we need money to actually do it. And for the first time, the government was like, hey, let's do that. So
Right.
I don't know
And
enough
so you said
about the
since World
space
War
stuff.
II.
Yes.
Yeah, well, we can. I mean, if you want, let's wrap all of the like space like into flight. From the 1900s, we'll
Okay.
call human flight, as broad as that is,
But again,
and wrap that
that's
up into one box.
like an engineering thing versus like a more raw, much less practical
A science thing.
science. Um, but I would
Right.
put it.
So when did this stuff? You said in the 1900s. Like, when did
Mhm.
we first start identifying plate tectonics?
We will get there, but first I want to help people
Okay.
understand what it even is, because everybody sort of has a rough idea of what it is, but not that many people actually truly understand how it works, which is the goal of
Okay.
today. I want the science first, and then we'll do some of the history that I know you want later. So,
Yes. Okay.
to you, what is plate tectonics?
Plate tectonics was the idea that the Earth's crust was split up into different what were called plates, and those plates were able to, you know, I'll use the word glide across
Okay.
the Earth's layer of magma, um, and uh, I think that's actually the more or less what I want to go with there. The Earth's
Okay.
crust is not one solid layer, but it is cracked up into different pieces and is able to glide along the magma. I've heard other things say, and this is significant because this and that, but
Hmm.
just what is plate tectonics? That's what I'm going with.
So that is, I feel like a pretty good, um, like where the general public would be at with plate tectonics, and that
Okay,
is more or less true. Like there was nothing glaringly wrong with it.
right. Okay,
But obviously we're here to get a little bit into the weeds. Um, so according to several different definitions that I've looked up, uh, the general definition of it is that plate tectonics is the scientific theory that describes the large-scale motion of tectonic plates that have made up the Earth's lithosphere for the last 3.3 to 3.5 billion years. And so you'll notice that I didn't use the word crust in that.
Right.
Because most people kind of know, or if you've ever seen a lot of like sci-fi movies, you'll know that there's like the Earth's crust, then there's a layer that's called the mantle, then there's the outer core,
Right.
and then the
Yes,
inner
mantle.
core. Yes, the mantle is
I think I forgot.
the like what you call like the magma underneath.
I meant to say mantle, and I just the
That's
word
okay.
blanked on me.
But we're gonna get a little geology 101 here. So
Perfect.
the four layers that most people are familiar with are, like I said, the crust, which is the very thin, hard, rocky outside layer of the Earth. Generally, it's a little less than like 10 kilometers thick in the oceans, and then somewhere around 30 to 35 kilometers thick on the continents. Below that is the mantle. The mantle is very often described as plastic, in that it exists it is mostly solid, but exists in this weird large-scale state that it behaves a lot like a liquid, sort of like glaciers do, where it's like a glacier is solid, it's ice, but it flows like a river does, just at a much slower speed. So if you look up like mountain glaciers, they look like just gigantic rivers, because that's pretty much what it is. So the mantle is kind of plastic in this same kind of way. It is warmer, much warmer than the crust, but not quite enough to be magma, as most people would think about it. It's not like the flowing stuff that you see coming out of volcanoes. But it is still very, very hot.
Okay.
And this is generally...
Is that because of all the pressure that it's under? Like it's more solid because of the pressure?
No, it usually just isn't hot enough. That probably contributes to it a bit.
Okay.
But it is hot, but not hot enough. Well, and I'll get into some temperatures here in a bit.
Gotcha.
So the mantle is generally sort of split into the upper and lower when you're talking about it in like research papers and things. So the upper mantle is... So for reference, I said at its thickest, the crust is only maybe like 40 or so kilometers thick. Granted, it's kilometers here, so this is pretty thick.
Right.
And I was not kind to myself, and I did not put the freedom units on here, so we're dealing with kilometers today. So yeah, the upper mantle compared to the crust is around 665 or so kilometers thick. So it is at least 200 times thicker than the crust. And the lower end of the upper mantle is around 700 kilometers below the surface. The lower mantle is around 2,200 kilometers thick. And the lower end of it is around 2,900 kilometers below the surface. So almost 1,000. Nope, that's not math. Almost 100 times the thickness of the mantle, or the crust. Down toward the bottom of this is where it's really hot and where it melts occasionally. And the reason for that is because right there, underneath the mantle, we have the outer core. It is a liquid, and we know that through various physics reasons. Earthquakes produce two different kinds of waves that go through the crust. One of them can go through liquids, the other one cannot. And so if you have an earthquake at one location, you will get the one kind of wave that can go through liquid directly on the other side of the planet. If you had like a seismograph, which is the type of instrument that measures earthquakes, you would get those waves directly going through it. But in order to get the type of wave that cannot go through it, it has to be sort of reflected, which does happen, but you can tell that it's reflected and not like a direct measurement. So it's weird in that the waves get like sort of reflected or refracted, I think is the technical term. Like if you like when you're looking through water, how light gets
Right.
refracted a bit. A similar thing can happen with the earthquake waves. So again, I'm not like a physics person at all, but trust me here, we know for a fact that the
Mhm.
outer core is liquid, and it is really really hot and mostly made out of nickel and iron. And when I say really, really hot, this time I actually did put freedom units here. So it is around 6,000 degrees Fahrenheit on its outer surface.
Is that? I mean, how hot is the surface of the sun?
Um, Somewhere around 10, maybe a little less than 10.
So I mean, we're approaching that.
Yeah. And uh, at its sort of boundary with the inner core, this is a number that I am not at all a geophysicist or anybody who studies the deep earth like this. So I'm taking this with a big grain of salt, but I saw this in a couple places, so it must be kind of reputable. At the
Mhm.
lower boundary, right up against the inner core, it could potentially be up to around 14,000 degrees Fahrenheit, which is hotter than the sun. At least the surface of the
And how
sun.
deep again is this? How
At
deep are
this
we
point,
talking? Where we're? Yeah.
yeah, at this point, so the outer core is around 2,300 kilometers thick. So basically as thick as the entire mantle, a little less thick, but very close. And where the outer core meets the inner core is around 5,150 kilometers below the surface.
Wow.
Yeah. And lastly, we have the inner core, which is solid because of all the pressure of the rocks above it. It is definitely hot enough to be a liquid, but there's so much pressure from the thousands of kilometers of rocks above it that pressure compresses it so much that it cannot turn into a liquid. At least
Wow.
that is what I have been told. Once again, this is not at all what I do. So after this, I get much more confident
Right, but you're
about,
trusting other experts.
yes, I'm trusting other experts, as you should, because this is what they spend their entire life doing. Um, so it is also mostly nickel and iron with some other elements that are most likely extremely radioactive. Because from most things that I've seen, the Earth would be much cooler and we wouldn't see a lot of the things that we see, just like the physics of a lot of the things inside the Earth break if there wasn't a ton of heat being added from radioactive elements. The physics just doesn't work. Obviously, we have no
Right.
samples of rocks from that deep in the Earth, so we don't know that for sure. But the physics strongly suggests that there is some kind of extreme radiation inside the Earth. Uh, so it is likely also around 10,000 degrees or so, degrees Fahrenheit, and at the
Hmm.
center of the planet. So this would be as far inward as you can go until you start moving out again, is around 6,371 kilometers below the surface.
That's specific.
Yes, and that varies a lot depending on obviously where you are. I'm assuming that they're going from like sea level, because obviously if you're on
That
the
would be
top
my
of Mount
guess.
Everest, it's a lot different than sea level. Uh,
Right.
but that is the number that I was given, or that I saw in a couple places. So that is the Geology 101 version of the layers of the Earth. However, these four layers are only part of the story for plate tectonics, because as I mentioned during that definition, I didn't mention crust or mantle at all. Instead, there are a couple other layers that are kind of combinations or only parts of the other layers. So, for example, the lithosphere, which, litho means rock. I believe that's in Greek. But basically the rock sphere, which doesn't really help because it's all rock. But anyway, so this is the crust plus the topmost part of the upper mantle. So there's a bit of overlap in the lithosphere between the crust and the upper mantle. But it is all solid. Completely solid. It varies from around 10 kilometers thick at like the newest ocean crust to potentially over 200 kilometers thick in some areas of like really, really thick continental crust. Places like the center of North America, around the Rockies. Places in like central area, like around Mongolia. So it can be very thick, but generally somewhere in between those two sort of extremes. And that is what the plates are made out of. They're made of the lithosphere. So it's not like the crust is sliding around on top of the mantle. There's not like a super clean boundary there. But there is a pretty clear boundary between the lithosphere and the layer below it, which is called the Asthanosphere. This is the part of the upper mantle. So this is
lithosphere.
Oh, go ahead.
But, No, I haven't heard
yeah,
of that.
this is not,
but not the Asthanosphere. That's a new one.
Yeah, this is not one that's really talked about that much, just because most people use crust and lithosphere kind of interchangeably, and like technically they are not the same. But for anybody who doesn't work with this stuff specifically, like even I don't really need to know the difference between the crust and the lithosphere. I should, any geologist should, but it's like for my day-to-day things, the technicality between crust and lithosphere is not important to me, just because I never go that deep. Nothing, no rocks that I work with have really been that deep. So most people will say lithosphere when they mean crust, and therefore gets kind of thrown into the, regular talk much more commonly than the asthenosphere does, because the asthenosphere is only a part of the upper mantle. So it's not, it doesn't go into the lower mantle at all, and it's not even all of the upper mantle. So it's just a portion of the upper mantle. So it is the portion that sits directly below the lithosphere. And I was not able to find a really good sort of answer for exactly how thick the asthenosphere is. Apparently we don't really know. Which I'm like, okay, then why not just call it? I think the only reason that we have the term asthenosphere to begin with is because that top portion of the mantle is the lithosphere. So it's like, well, we need to call it something else. We need to, so that we know we're not talking about that part. We're talking about the part under it,
That's just so wild that there's not an estimate.
Because I don't know, like what term they would use to define the underside of it. I saw some sort of things argue that's like, okay, it's as deep as tectonic plates go, and we'll talk about that in a little bit. But when tectonic plates get sucked underground, essentially, or deeper underground, I guess, as deep as they go, the lowest that they physically can go should be the bottom of the asthenosphere. But it's like, okay, how do you measure that? How do we know? Like, that's a really hard thing to quantify. So
I guess that makes sense, actually.
That's the best answer that I could find, but it did not give me a depth estimate. So do with that what you will. Very unsatisfying.
Understood.
But we're moving on. So those are the two areas, portions of Earth's interior that are important for plate tectonics. And so while we're talking about plate tectonics, we should talk about what exactly are tectonic plates even. So that was included in that definition that I gave. But what even are they? And I think you did a pretty good job where it's just sort of like sections of the, you said crust, but as we now know, lithosphere, that are just sort of floating on top. And that is more or less correct. So they are basically just slabs of lithosphere that float on top of the asthenosphere because they are less dense. And I specify that because, if something floats, it's very much implied that it is less dense than whatever it's floating on, right? Cork floats on water because it's
Right,
less
but it's good to
dense.
say it.
Right. And it's
Yeah.
also incredibly important because everything in plate tectonics revolves around density and differences in density, even really small ones. So that's basically just what tectonic plates are: slabs of lithosphere. A relatively simple concept. And where they bump into each other and how they move is where it's of interest to us as humans, because that affects the things that we do. And so, as we sort of got into last episode, I want to talk a little bit about plate boundaries and types. We're still doing a little bit of Geology 101 here. So there are 3 different types of plate boundaries. There is convergent plate boundaries, where 2 plates are both moving toward each other. And in that case, generally, a continent is, continental crust is less dense than oceanic crust. So if it's a continent running into an ocean plate, because there are plates that are completely in the ocean, don't have any continent on them.
Right.
The continent, because it's less dense, it will sort of push itself on top of the oceanic crust. In that case, the oceanic crust is what's called subducted, meaning that it's just brought under another plate. Then there is divergent plate boundaries, which are the exact opposite, where plates are moving away from each other. And when that happens, at that spot where they are moving away from each other, new crust is created and brought to the surface from within the Asthanosphere. And then there is transverse plate boundaries, where they're not moving toward or away from each other, but they're sort of sliding past each other, like sandpaper, almost, if you were sanding something. Or if you rub your hands together, like your palms together, just rub them together, that's a transverse plate boundary, essentially. So those 3 are very important, mostly the convergent and divergent, because we're going to talk about them later.
Right.
So obviously, for these kinds of plate boundaries to happen, plates need to move. But if you're talking about literal continents, what could possibly provide enough force to move an entire continent, So
Other continents?
sometimes, but what pushed that continent into what pushed continent A into continent B?
Oh, interesting. Okay.
So we don't really have a perfect answer to that. We have good answers, but not a perfect one. So initially, like I said, in the definition, plate tectonics has only been happening for the last 3.3 to 3.5 or so billion years. But there's about 1 billion years worth of Earth's history that was before that. So what sort of kickstarted plate tectonics to begin with? And so we think that it was... are you familiar with convection currents, Mike?
Yeah, isn't that? I mean, there's ovens, and then
Yep.
there's that also happens, I believe, in the mantle, where it's warmer magma or water or whatever will rise, and then the cooler one will fall, and it sort of creates like a circular cycle inside of
Exactly.
whatever it is you're talking about. Is it okay?
Yeah, that's exactly right. So imagine if you have like a pot on a burner. The water at the bottom
Right.
will become hot and will rise because it is less dense. Heat rises because it makes whatever is getting warmer less dense, and therefore it rises.
Mm-hmm.
However, when that water rises, some water has to move in and fill where that now warmer water just was. So it pulls water from the top of the pot down toward the bottom. Then that water warms up and creates sort of a middle of the pot flowing water up, and then the water flows out to the sides and then flows back down to the bottom. That is a convection current. And that is pretty much
Right.
what we think kickstarted plate tectonics. Magma from down in the very bottom of the mantle, down around the outer crust or outer core, got really hot and would
Mm-hmm.
rise to the surface of the Earth, or at least very close to, the Asthanosphere. And that once it hit, the wall that is the lithosphere, it would spread out. And we think that those convection currents are what started off plate tectonics. And
When you say started plate
mm,
tectonics, you mean started like the movement of the plates, not like, cracked the lithosphere, correct?
I don't know if we know the answer to that question. I know that I
To
don't
which
know the
question?
answer to that question, but I don't know if science knows the answer to that question.
To which question?
Whether the plates were already cracked when that started, or if the lithosphere was solid and that created cracks. Although I will say,
Gotcha. Okay.
the plates that we currently have today were not always the same plates that have always been around.
Really?
Yeah. So, for example, I think the oldest ocean crust is, I want to say, I think I heard, because I was listening to another podcast about this earlier. I want to say like 180 million years old is the oldest ocean crust. So, new ocean crust is being made
Which,
all the time.
yep.
So, and like, for example, the Pacific plate, one of the biggest, is completely ocean, to my knowledge. I don't believe that there's any continental crust. There is landmass on it, obviously, like Hawaii, but the Pacific plate has only oceanic crust. So, at maximum, the Pacific plate is 180 million years old. So there were
Right.
more plates that took up the Pacific plate sort of space on the lithosphere before that. So I don't know whether the plates already were broken up and stuff or not, or if this was what broke up the lithosphere into the first plates. I don't know that. But that was a really good question, though.
Okay. Yeah, fair enough.
So yeah, that's what we think sort of kicked off at least the starter motion of plate tectonics. But we think that today, most of the ocean, or most of the movement is sort of driven instead by subduction, like I was mentioning earlier. So if a continent or a plate is sinking underneath another one, that's a lot of material that's basically acting as an anchor at that point, dragging something down. So,
Mm-hmm.
for example, in certain parts of the boundary between the North American plate and the Pacific plate, the North American plate is moving over top of the Pacific plate. And therefore, it's pushing the Pacific plate down into the Asthanosphere. That pushing, and then once it's far enough down, gravity is just doing its work and pulling the Pacific plate more down into the Asthanosphere. That pulling and pushing motion is what is moving the Pacific plate, not really a convection current anymore. So it's like it's being dragged by the part that has already been subducted. Does
Mm-hmm.
that make sense?
Yeah.
So that doesn't give a perfect answer for a lot of things, though. Like, for example, the North American plate is definitely still moving. However, it is not being subducted in a major way pretty much anywhere, yet it's still moving west. And so, if it's not being subducted anywhere, where is it getting that force from to be moving it west? And we don't really know. It could be more convection currents, but that's kind of tough to say.
Yeah, it's where did it all start from? That it's yeah.
All right, it's not like you can stick a camera down there.
Right. Right.
So
Not yet.
uh, that's a big not yet, potentially a not ever.
Yeah. I
Because
probably not ever.
right, because even the
Well,
upper
I don't know if I believe
mantle
that.
is still many hundreds of degrees Fahrenheit.
Yeah, that'll be a ways.
Yeah. So that is generally how we think they move. Not a complete answer, but it's what we've got right now. And it's good enough
Right.
that, just because something's, like I said, a theory and has so much evidence supporting it doesn't mean we know everything about it. We absolutely don't know everything about evolution. Not even close. We have enough to know that it works. We have enough to generally know how it works. But there's, as always in science, lots and lots of questions that still would be cool to answer.
Right.
And so, also, as we were sort of talking about last episode, I want to talk a little bit about faults and earthquakes, and then something called active and passive margins that sort of determine, today anyway, where earthquakes and volcanoes happen. So, do you remember what I said about faults last episode? If you don't, I don't blame you. You have a lot going on.
No, because I remember my idea of a fault was always that it was the boundary between two different tectonic plates, and you told me that that was incorrect, and
Yes.
I forgot what you corrected me and said it was.
Well, because if you watch any piece of media, I'm looking at you, San Andreas movie with The Rock, you would think, and granted, I haven't seen this movie, so I don't know if they actually correct this in the movie or not. I have no idea. But you would probably think, like Mike, that if, that a fault is the same as a plate boundary, which it's not. So a fault is literally a crack in some rocks with one of the sides of the crack moving up or down so that they are no longer even with where they were. There's also another feature in geology called a joint that is a crack that doesn't have the movement aspect to it. Sometimes you can get just a big crack through several layers of rock, like well below the surface. That just doesn't have enough force. It has enough force to like cause the crack, but not enough to like significantly displace the layers. So, yeah, that's another term that you may come across called a joint. But so earthquakes, actually, before I get to earthquakes, faults tend to happen a lot where there are plate boundaries, just because that's where a lot of the force is. So for example, the most of the Pacific coast of North America is, like I said, a convergent plate boundary. So North America is moving on top of the Pacific plate, and that stress that all that force is causing sometimes causes faults because the rocks just are not structurally sound enough to withstand all of that force. When that happens, faults can sometimes cause earthquakes if they're big enough, and location kind of depends a lot too, of how close it is to the surface. So sometimes if the stress of the two plates crashing into each other results in a fault, that can sometimes cause an earthquake. However, earthquakes are also sometimes caused by, so say the North American plate, like I said, moving on top of the Pacific plate, gets a little stuck, but obviously with so much momentum of the rest of the entire continent of North America pushing behind it, the force still keeps building up. And then eventually it will get unstuck, and the edge of North America will slip back to, like, basically get unstuck, and then that really fast motion of the plate back up to where it should be if it hadn't gotten stuck, that also that's what causes like the major earthquakes. So that is,
When you say major, like how big is major?
I don't know. So I'm not all that familiar with the Richter scale, which is sort of the scale that measures earthquakes. Oh, my neighbor's dog is outside. I'm so sorry. She's really cute though. So just imagine, like, basically she's not a golden retriever, but imagine a very small golden retriever. But so I know the Richter scale is logarithmic, meaning that a 2 is 10 times stronger than a 1 on the Richter scale.
Right.
So faults can cause anywhere from like around 3.0, 3.5 earthquakes But like your major ones, like ones that destroy cities, those are probably the ones caused by this plate slippage instead of faults. And off the top
Right.
of my head, I
Okay.
don't know what how powerful the one that recently hit Haiti was. I don't know what that was off the top of my
Oh
head, but they
goodness, I
are
forgot about
on
that.
a plate boundary. Um, but yeah, if you have not heard about that, please look it up. It's and if you have any spare money, please send some money to some kind of non-governmental organization that's operating in Haiti right now. They really need it. Um, but yeah, so that is sort of how earthquakes form. But you'll notice much more if you look at like an earthquake map. You can almost perfectly look at plate boundaries by looking at earthquake maps. And this is because of what else I mentioned about being an active versus a passive margin of a continent. So if you look at the North American plate, for example, just because that's what I'm most familiar with, the western side has lots and lots of earthquakes because that is where a plate boundary is. And that's also why the Pacific Ocean gets very deep, very close to shore on the west coast of North America, whereas on the east coast, there is not a plate boundary. And the ocean generally slopes very little as it gets deeper. It's not like a really steep drop off, it's a nice gentle slope. That
Hmm.
is a passive margin.
I did not know that.
Yep. And that is why there are very few earthquakes in, like New York, say, as opposed to, I don't know, California. um,
Mhm.
and if you look at South America, that is basically the exact same case. The western side is a plate boundary, whereas the western side, or the eastern side of the plate, extends well into the ocean, way out into the Atlantic. So if you look at earthquake maps and things like that, you will see lots and lots of earthquakes in western South America, but not so much on eastern South America. So that is the last of the sort of Geology 101, here's facts about the Earth that I want to talk about. So now we'll get into some of the history, because it's really interesting
Okay.
history. So people had noticed that the continents kind of look like they should fit together for quite a while, um, especially South America and Africa is the one that's always very much pointed to, where it looks like a puzzle. It looks like they literally fit together like puzzle pieces.
That's the
And
obvious one.
yes, that's a very obvious one. There's some other obvious ones, sort of like very northern North America, kind of looks like it fits a bit with Scotland, but that's much less obvious. But people had noticed that even back to like the late 1500s, with how bad our map making skills were at the time relative to today. People knew that even back then. And it's really funny. I ended up finding a quote from Benjamin Franklin
That guy.
hypothesizing about why this might be. So, this is a direct quote that he wrote to a geologist, a French geologist, while he was living in France back in 1782. So, direct quote from Benny Frank here. Some part of it having been depressed under the sea, and other parts which had been under it raised up. I hate reading Old English.
Oh, yeah. It's the worst.
Such changes in the surface parts of the globe seem to me unlikely to happen if the Earth were solid to the center. I therefore imagine that the internal parts might be a fluid more dense than any of the solids we are acquainted with, which therefore might swim in and upon that fluid. Thus, the surface of the Earth would be a shell, capable of being broken and disordered by the violent movements of the fluid on which it rested.
I mean, it seems like he kind of had it down.
Pretty close. And really, nobody would come close for like another 150 to 200 years. So
Wow.
Ben Franklin is really doing a lot of cool things out here. I thought that was so neat when I found that quote.
I mean, you know me. I love that.
Mm-hmm.
That's awesome.
I know, and I also definitely threw that in there for you too.
Much
um,
appreciated.
but yeah, so once geology and paleontology really started getting into like the modern age, sort of at the turn of the 1900s, um, people really began noticing that not just like the continents sort of look like they fit together, but if you look at like Eastern South America and Western Africa, the rocks are really, really similar. And the fossils are really, really similar. And so they're like, well, this is a little weird. How do we explain that? And this is sort of before they had, evolution wasn't a thing at this point. So they were like, I maybe they just happen to be the same. I don't know. But they didn't have a great explanation for it at the time when they first started looking at these things. And in particular, some of the rocks that I wanted to point out, because anybody who might remember our like mammal ancestors, or like the evolution of mammals episode, will remember the one particular genus that literally took over the world after the end Permian mass extinction, called Lystrosaurus, the one that was like 95% of all fossils in the layers that it's found in. That Lystrosaurus was a real key factor in sort of figuring out plate tectonics, because you find its fossils in Africa, Australia, India, Antarctica. So it's like, well, this is a real weird thing to find in all of these places. As well as sort of a...
Yeah, I wonder if there's an explanation for that.
Oh, yeah, I wonder. So they had come up with some interesting hypotheses that we'll talk about a little bit in a second. But the first one who sort of got it pretty close to right, and who is sort of credited, perhaps incorrectly, as it potentially should be Benjamin Franklin, was sort of credited as the father of plate tectonics, is a German scientist named Alfred Wagner. And
look, Benjamin Franklin has enough to his name. He's already
yes,
on the $100 bill. Like, we'll give this German dude his credit.
Right. So he, as sometimes happens with sort of the first person to come up with the right idea in science, if he's the first person, it's not like he's saying something that's widely accepted, So
Yep.
he was pretty much dismissed out of hand as soon as he published his stuff. And so he published his first piece on it in 1912, is when he first proposed it, and then further expanded on it in his book in 1915 called The Origin of Continents and Oceans. And I really think he was trying to grab some attention with that as the title. So he proposed that the continents were once all combined into a single landmass, which we now know is true, and that they had since floated apart. He proposed that the less dense granite of the continents floated like icebergs on like a sea of basalt. So like I said, the continents mostly are made out of granite. Oceanic crust is made out of basalt, which is more dense than granite. So it makes sense that they would float, and he compared them a lot like icebergs, like I said, which we now know is not quite true, but for the time was the closest anyone had really gotten thus far. And like I said, he was really not accepted by other scientists, especially in the northern hemisphere. So like all of the scientists in like the United States and the rest of Europe really didn't buy it. But weirdly, a lot of the scientists in the southern hemisphere, in like South Africa and Australia at the time, pretty much went with it, especially the ones in South Africa, because that's where a lot of these fossils that are found in all those other continents are found as well. So a lot of them were like, well, it's right here in our backyard. Maybe you should kind of trust us to talk about our own geology. But whatever. And basically for the next 50 or so years, science kind of fumbled to explain the evidence that Wagner had laid out. And there had been a couple of other hypotheses, like one that I don't actually have in our notes here, was that the Earth was expanding. That sort of like, if you were to draw Pangea on a balloon and then blow up the balloon, the continents would sort of spread apart, right? That's the
I mean,
idea
if
that
you
they went
don't know
with.
what's going on,
There was very little evidence to actually support that, obviously. But that was an idea that had been thrown around.
I mean, look, that sounds really dumb to us now, but you know what? If people don't know what's going on and they're just throwing stuff against the wall, you know what? That I
Right, but it's
suppose that is an okay thing to
there.
pick and then
Mhm.
disprove.
But it's very much a solution that fits a problem that fits a solution instead of a solution that fits the problem. You know, so
Yes,
it's like this is
that's
something that
correct.
would explain it, but we have no evidence for it. Instead of hey, here's this thing that explains the evidence that we see. So again, there was literally no evidence to support that, obviously. Um, but the only really prominent hypothesis that I could find that was really heavily debated that there was large land bridges that would sort of pop up, maybe due to some kind of volcanic activity that would connect the continents like roadways, essentially, that would allow these animals and plants to move from continent to continent. Um, and so this was what was really sort of in vogue during, um, before, during, and a little bit after World War II. Obviously, we know that that's not really true. That's a weird, like, it would explain it, but again, we don't really see any evidence for that. And then,
Right.
it, as with a lot of things uh, around war, war creates a lot of new technology. And so, with all of this technology that was made for doing war, uh, it was then co opted for use for other things, which is nice. That's how the internet kind of got started and how GPS got started. And in the case of World War
Yeah.
II, that's how things like sonar and a lot of like magnetic monitoring in the oceans got started.
Mm-hmm.
Yeah. Mostly looking for other submarines, like mostly in the Atlantic Ocean, but also in the Pacific Ocean as well. And from all those new
It's one of the things
technologies,
that, like,
yeah,
I was just gonna say, like, with war, that's nobody likes to admit it because, like, it's not the point. But there are some advantages to war, and the
yeah,
advancements that come from,
hmm
it is it's undeniable, even if not the point.
right, absolutely. And so in World War II, submarines were equipped with, at the time, very, very new sonar. Sonar was not really a thing because it's like, well, what would we need to look in the oceans for? You know? Um,
Mhm.
so they were starting to make maps of the seafloor to better navigate themselves because GPS wasn't really a thing yet. So they had to navigate based on maps of the seafloor. And things that they kept noticing in the Atlantic and also in like the Southern Pacific as well were massive mountain ranges under the ocean, basically halfway uh, going north south in the Atlantic. And by massive, I mean like not necessarily super tall, but stretching basically from like northern Greenland all the way down to about the same latitude as like the southern tip of South America, the entire Atlantic Ocean. Just this long, long, long stretch of basically mountains. And they also noticed with these mountains that there was this sort of ridge going down the middle of them. And it was
Mhm.
basically like they sort of, some people, geologists, because there were actually some geologists in the militaries as well because of drafts and things like that. Uh, but some of the geologists that they also brought with them were like, that it kind of seems like that they're pulling apart right there because it was be one mountain range and then the ridge, like the dip in the middle, then another mountain range on the other side, almost as if they had been pulled apart. Which spoilers, they kind of were. Uh,
Ha ha ha.
because so in the Atlantic Ocean, there's a feature called the Mid-Atlantic Ridge, and that is a divergent plate boundary between, at least in the northern part, the North American plate and the Eurasian plate, where they are moving apart. So Europe and North America are moving farther and farther away from each other all the time. And like I said, they also found the exact same thing sort of in the Pacific Ocean as well. And they also detected lots and lots of earthquakes around these areas as well. Surprise, surprise.
Mm-hmm.
And with all of these data and observations that they were finding, it was kind of hard to deny that there was something going on there. And then people started re-examining Wagner's work and realizing, okay, this is, he didn't quite have it right, where it's not like they're floating like icebergs. You know, the part of the Atlantic Ocean that is next to North America is still connected to North America, but it is not connected to Europe. It is not connected to South America. It is its own isolated thing. And if you look at earthquake maps, you can literally see where each one starts and stops.
Where's this
And
again?
when is this, you said?
Where?
Where? So pretty much everywhere by this point.
Okay.
You mean like where are the scientists working on this, you mean, or?
I mean, like where could we be seeing this around the Earth? But if they're happening everywhere, then
Yeah, so it's like anywhere that there are plate boundaries, right? You get lots of earthquakes. So around this
right.
time, like people had sort of been making earthquake maps for a little while as soon as they had the technology to do so. And
Mm-hmm.
then it sort of clicked. Okay, we see a lot of earthquakes here. This is probably why. And so it sort of started off in the early to mid 1960s with a concept called seafloor spreading, which is what is happening between Europe and North America. New crust is being formed at that ridge and pushing the two apart. You know, the seafloor literally is spreading itself. And so
Yes.
they were like, well, if new crust is being formed here, it's not like the crust is getting bigger, so where is it going? You know, if new crust is formed, some crust has to get destroyed, right? It's a
Right.
pretty closed system. So then they started looking at what we now call today as the plate boundaries. And we're like, that's probably where it's happening. And then as our technology got better, we sort of started actually going and being able to see this. So around the late 60s is when sort of the first subduction zones were first truly discovered. And then we had a basically complete answer as to, okay, yes, the continents do move around. They exist on plates. And it changed everything that we know about the science of geology.
I was gonna
Because
say about that time is when this got mainstream acceptance.
yes, around it, and as the 60s went on, it got more and more, especially as better, civilian scientists were able to access all this, formerly high grade military technology. And so it was throughout the 60s is when it really became much more concrete. And when I say this changed everything in geology, I mean literally everything. Every part of studying the planet now made much more sense. Why do you see fossils and rocks that are the same on continents that are now thousands and thousands of kilometers apart? Climate science got changed so much because if if Antarctica wasn't where it currently is, the Earth would be like 10, and because it's really hard to grow glaciers in the water. You basically need a continent there for the snow to fall on to create all these big glaciers and lock up all that water to lower sea levels. And then ice, because ice is really reflective, it reflects a lot of light back into space and reduces the heat of the planet overall. And so if Antarctica didn't drift, continental drift, if it didn't end up through plate tectonics where it currently is, the Earth would be a lot warmer than it is today.
Wow.
And not just that, but it's like mountains affect climate so much. Like the Himalayas, I think we've talked about this before. The Himalayas affect the global climate in ways that we don't even understand. It just having mountains that high and that large of a mountain range affects like air currents in like the upper atmosphere in ways that are really, really hard to understand. But plate tectonics explains why there are mountains there. Plate tectonics explains why we have volcanoes in Iceland and Greenland and around the Mediterranean. It explains why earthquakes happen in places like Haiti but not really in places like New York. It explains and puts everything in geology into so much context that, again, you can pick up a rock and fully understand that rock as to its properties, but you can't understand anything about how that rock is where it is, or even why its grains are the size that they are without understanding plate tectonics. So when I say that this is like
It
the
really is,
most
like you said.
important, this is the most important
Yeah,
thing in geology by far.
it's one of those fundamental things that just you cannot advance any further until you have that understanding of plate tectonics and what it is, what that means for the entire field.
Exactly. And we had a running joke and so we had 5 full-time faculty members at my undergrad school at SUNY Cortland. Go Red Dragons. So we had a paleontologist who was my advisor. We had a like hydrogeologist who studies groundwater, a mineralogist who studies minerals, um, a surficial geologist who studies mostly glaciers, but also things like rivers and landscapes. And then we had a what was her actual title? Like sort of like seismology. She didn't quite study earthquakes, but not quite geophysics either. Like she's a structural geologist who studies why rocks are like bent up in the shapes that they are, mostly from past continental plate collisions. Uh, but so in her class was sort of where we learned most of this stuff. But we had a running joke, regardless of who was teaching the class, regardless of what the subject was. If you didn't know an answer on a test, if you put plate tectonics, there's like roughly like there's a not insignificant chance that you would be right somehow, and that you could argue that for some points. Because so much so that like so one of my teachers, my our paleontologist who also did a lot of work with like sedimentary rocks, he once took us on a field trip going from east to west across New York State. And again, this was not a class about tectonics. This was not a class about geophysics or anything to do with like deep rocks. This was all, sedimentary rocks. And none of it would have made sense, this field trip, because he basically used this trip to tell a story where it was when we were in eastern New York, was sediments, really coarse grained sediments from when Laurentia, the northern supercontinent that would later go on to form Pangaea, when that was together, when Europe and North America were buddy-buddy. But during that collision, there were really, really high mountains just to the east of New York. And so those mountains created a lot of sediment. And because in eastern New York, we were really close to the mountains, the sediment was coarse because it was like fresh and hadn't been eroded a whole bunch. But then as we moved west, it got to like deeper ocean sediments as we went farther west. And it's like, how do you explain that if not for plate tectonics? There's a very clear observation that all from roughly the same age had similar fossils in them, but there's no way to explain that without the context of plate tectonics.
What it makes me think is just like, so plate tectonics helps us, and it helps explain so many things that were just previously chalked up to we don't know, or had bad explanations.
Mm-hmm.
It kind of makes you think like,
Right.
What in the future is going to be just this very commonly known and easily understood phenomenon that explains so much of the things that we just don't have an explanation for now.
Mm-hmm.
It's just, the, the knowing that there's so many things that we don't know, but hopefully someday will, is, I don't know if humbling is the right word, but awe-inspiring might be what I would go with.
Yeah, absolutely. And like I said, given how much I don't understand about like space or like particle physics or that kind of thing, I'm sure that there are lots of these potential like nexuses, like how biology is like the nexus of biology. Plate tectonics is the nexus of geology. I'm sure that there is a nexus of particle physics out there somewhere that we haven't really found, because to my knowledge, we don't really understand like super, super fine particle physics that well. But we will eventually, and maybe in my lifetime, maybe not. But I really look forward to uh, seeing all these different advancements in other sciences that I can continue to not understand.
I could not agree more. And does that wrap up our episode on plate tectonics?
It absolutely does. Thank you for sitting here and letting me give you a lecture in Geology 101. Uh, but it's, like I said,
And
I'm kind of kicking myself that I didn't do this one earlier, because while this is mainly a paleontology podcast, paleontology is a field of geology, and understanding the rocks around the fossils is just as important, if not more important, than understanding the fossils themselves. And like I said, you can't understand the rocks without the context of plate tectonics. So I'm kicking myself a little bit for not having done this a little sooner in the life of this podcast. But we got to it eventually.
well, hopefully this podcast will go on for many more hundreds of episodes, and it'll be right at the very beginning for anyone who listens to us at that point.
Absolutely.
This has been episode 39 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Mike, and that was Gavin. Gavin, thank you very much. Talk to you next week, everybody.